And the reason is because Newton's law, right, which are behind all Hamiltonian systems, have an associated variational formulation, which are the Euler-Lagrange equations, and these Euler-Lagrange equations are in turn intimately related to symplectic structure by taking the Legendre transform and going to the Hamiltonian side. So this is the case if there is no irreversible process in the systems. Now, if we include irreversible process, if we are, for instance, in the Poisson formulation, there should be some modification of the Poisson bracket, right, to treat non-equilibrium thermodynamics. So several modification of the bracket, of the Poisson bracket, have been proposed, and you quickly see, if you open such a paper about bracket formulation in non-equilibrium thermodynamics, that there is no systematic way to derive these brackets. They have some precise axioms, but for instance, one system can have several bracket formulations, or sometimes the axioms change according to the system that is under study, etc. So the goal of this talk is to show that the variational formulation of thermodynamics that we presented can be used to derive in a systematic way all these things, at least 3 kinds of such brackets. So just to summarize the variational formulation of thermodynamics that we have developed, summarized from the previous talk. So keep in mind that it's an extension of Hamilton's principle, right? So in absence of irreversible process, you should recover Hamilton's principle. It works both for finite dimensional system and for continuum system, like thermodynamics of fluid or elastic media. And it's not only useful to recover known equations, but also to propose models that are thermodynamically consistent, and also to discretize in a geometric way this problem of non-equilibrium thermodynamics using variational formulations. As you have seen, the geometric structure behind that is the R-Dirac structures. There are other structures, of course, that have been proposed for thermodynamics. One of them are contact structure. There has been a lot of work. There is still a lot of work in this direction. Here are some important papers in this area. And for the bracket formalism, this started in '84 with these 3 papers by Kaufmann, Morrison, and Grmela. And then this was developed for several systems and several kind of fluid with microstructure, etc. So as I said, the situation is not completely clear from the point of view of the structure that has to be found from the equations. So the plan is the following. I start by reviewing the variational formulation for closed system. I leave the open system for another talk. Then I will review 3 kinds of bracket formalism that have been developed, and then how to derive them from the variational formulation. So things that I will not do are show how we use this variational and bracket structure to modeling and discretization, and I will not present the continuum system, just focusing on the simplest finite dimensional case. So just to give you a quick idea, these are some thermodynamical systems. The simplest thermomechanical system is this one, right? It's just one piston. This is the mechanical part, one-dimensional mechanical system. And one fluid here that you describe just by one entropy variable. So you don't describe the motion of the fluid inside, just its temperature or its entropy. Another typical system in this area is the diffusion problem between several compartments. So let's assume that you have one chemical species that can diffuse through this membrane here. So here the variables that you have to consider are the number of moles in each of these locations, the flux, the thermodynamical flux from one reservoir to the membrane and from the membrane to the reservoir, and also the chemical potential in each location. So this is the setting for diffusion problems. Another one is the case of chemical reactions. So this is a typical chemical reactions where here I suppose that only one temperature is attributed to the system. As a consequence, only one entropy also, and your dynamical system must solve for the evolution of each of the chemical component in each number of mole of each chemical component. This is an example of open system that has been already described in the previous talk. As I said, a typical example of a continuum thermodynamic system is the case of a multi-component fluid, right, that is subject to viscosity, diffusion between the various spaces, and also able to conduct the heat. So a main example of such thermodynamical fluid is the atmospheric dynamics, for instance. So this is just a quick review of the variational formulation in the simplest possible case. So you just have mechanical variables and one entropy variable. If you were doing mechanics, just take the critical curve of the Lagrangian of L of Q and Q dot. You get Euler-Lagrange equations. This yields symplectic structure, Poisson structure by reduction, etc., etc. Now, if you are doing thermodynamics, you have S here, the entropy. And to get the correct equation, the big step is to include constraints, a little bit similar to what you do in non-holonomic mechanics. So you have two types of constraints. One constraint on the critical curve, this is this constraint that we have seen in the previous talk, and one constraint on the variations of this critical curve that you consider in the principle, right? So you see that it's much harder than linear non-holonomic mechanics because this is a nonlinear constraint in the curve. Of course, it's linear in the variations, but it's nonlinear in the curve. This gives these equations. So the Euler-Lagrange equation with friction and force and the entropy equation here. Only the irreversible process of friction is inserted here, but other process can be also included. For instance, if I want to include other irreversible process, diffusion or chemical reaction or heat conduction, for each process I need to define a variable that we call the thermodynamic displacement, such that its time derivative is the thermodynamic force of the process. For instance, if you are doing diffusion, the thermodynamic force is the chemical potential. So define a variable W such its time derivative is mu. Similarly with the other process, if you are doing heat transfer or chemical reaction, each time you define a variable whose time derivative is this thermodynamical force. And this is a kind of mechanical analogy, right? When you attribute to each process a mechanical variable Q, whose Q dot is the thermodynamical force, right? So using these thermodynamical displacements, we were able to extend the previous variational principle to all kinds of irreversible processes. This is an example. For instance, you have a mechanical system with several compartments in which you have several one chemical component in several compartments that can diffuse. So the process that you use, the variational principle that you use is similar as before, but you have here two contributions, not only the friction force, but also the diffusion part here, which is the flux acting on W dot, etc., etc. So you get the equations of motion. Now, let me review the bracket formalism. So, as I said, there are three kinds of bracket formalism. The single generator bracket, in which you just modify the Poisson bracket by this term, which involve F and H, the Hamiltonian, and which satisfies these two conditions here, which basically say the first and the second law of thermodynamics are verified. There is so this is due to Veris and Edward. Then there is the double generator formalism, in which you deform the Poisson bracket using a something bilinear in F and S, not H, right? F and S, the entropy. You have also appropriate axioms that tells you that the first and second law of thermodynamics are verified. And there is a subset of the double generator formalism called the triplectic or generic formalism that impose in addition that this bracket here is symmetric and verifies these two conditions for arbitrary function, not only H and S, right, but here G and here H, right? So this is a quick overview of these bracket formalism that have been proposed. So now we will show how to derive in a very systematic way all these formalism using the variational formulation. So it's a computational exercise that I will present. So for instance, I start with the bracket number 1, the Edward Berries. So I take step 1, I take the result, the equation coming from the variational formulation in terms of L, and I take the Legendre transform like that. So I just Legendre transform, of course, with respect to the mechanical part. I leave the rest untouched, and I get this system. Then I just have to express the flux in terms of H instead of L. This is a minor step, but you have to do it. Then you compute, you look at what you get when you compute the time derivative of some observable, like F, and you observe that what you get is exactly this bracket FH of Edward Berries that satisfied exactly the axioms that have been proposed by them. And in addition, you have a constructive way to build this bracket, right? You recognize each term here directly from the previous example. So this works for all systems. It should be continuum or discrete, open or closed. You can always recover these kind of brackets in a mechanical way. I mean mechanical, in a computational way. Right. Now if I want to recover the double generator bracket, same step as before, compute the F dot, and now you have to look at what you get in a little bit different way, the same quantity but in a different way, because you want something expressed in terms of F and S, right? Not F and H. So the idea is to replace in what you get S by an arbitrary G, right, and symmetrize. And what you get, as before, in this situation is this expression here. And you directly see that the axioms are verified. So there is no more mystery in the double generator bracket, right? You just take what you get from the variational formulation, compute F dot, and symmetrize the answer in terms of G, not S, and S, not H, and you get the correct double bracket formulation, not double bracket, double generator bracket formulation due to Kaufman. Let me now go to the last one, the generic bracket. So the double generator bracket that I just found is not generic, because if you compute F, H, it's not 0. This is one of the axioms of the generic or triplectic bracket, what it has, right? It has to be 0 for any functional F. So in order to get a triplectic bracket, you have to assume that the thermodynamic flux, like friction or other flux, depends linearly on the thermodynamic force. For instance, like that. So in this case, you can insert these formula in the bracket, right? And you build a triplectic bracket simply by taking what you got from the double generator bracket. I hope you still follow what I'm doing, right? I'm taking what I got from the previous exercise, and I subtract this term that is non-zero here to get 0. This seems artificial, but I do this, and I replace S by G, right? I organize a little bit the answer, and what I get is the metriplectic bracket, right, for this system, directly from a simple computation. And it's easy to check that the axioms are verified. So this works for fluid dynamics. The same process works for fluid dynamics, both in the Lagrangian or Eulerian framework. But it's enough to understand this bracket because it has the same structure. So let me conclude. So this variational formulation is very useful to derive this bracket formalism. And as I said, so far it was not very clear in how, given some PDE or some ODE, you can find such a bracket formulation. It's also interesting to compare the various brackets because, for instance, if you take the single generator bracket, you see that the bracket itself does not depend on the age of the system that you consider. This plays an important role in application. So this bracket is a more universal, right? The structure itself applies to H and S or any other functionals. And also you can include some nonlinear thermodynamic relation, something you cannot do with the metriplectic bracket. The double generator bracket intrinsically depends on H, right? The formula itself for this guy depends on H. Even if it's not written, should be parentheses index H. And still you can allow a nonlinear dependency on the thermodynamic force, which is not the case for the metriplectic. And so as I said, the similar derivation works if you have a non-simple systems, if you have several, you interconnect several systems, each of them has its own entropy, you can still write a bracket. And as I said already, it works also for continuum systems. So I let you see some reference that we wrote on that, and thank you very much.